So good morning, everyone. I'm here to talk about blockchain technologies and some of the work we have been doing at the Aarhus University and the Concordium Blockchain Research Center in this space. This talk will be much more from the ground up description of what blockchain technology is all about. We won't talk much about applications, but I expect to talk about the technical building blocks. So to start, I'm an associate professor here at Computer Science. My main research is in cryptographic engineering, which is the art and science of developing efficient and secure cryptographic algorithms and implementations to use in the real world. So it's very much applied and hands-on. But I'm also affiliated to the Digit Center for Digitalization, which is an entity here at Aarhus University that congregates researchers from several different areas, and to the our local blockchain research center. So I always like to start talks on blockchain by giving my personal stance on cryptocurrency. I think it's a fascinating research subject. It touches many different aspects of cryptography. It creates many applications actually for protocols we know for a long time and were not very useful in practice. So it's absolutely fascinating in that regard. But it's also a fascinating economic experiment if you look at Bitcoin and other cryptocurrencies, because you can experiment and see how the market reacts to new use and manipulations and speculation and so on, with damage kind of being contained to that micro space. So at least you're not interfering with currency of a whole country, but you can still study economic effects on this not isolated, but at least microcosmos of transactions and its own economic rules. My interest is purely technical. I have no financial stake. I don't hold any particular cryptocurrency. I just like the topic as a technical one. And to be sincere, I'm somewhat of a Bitcoin blockchain skeptic. I think the technology is really hyped, and there are many applications and that the enthusiasts think will be completely dominated by blockchains. And I don't think it's that easy. It's that simple. I think there is some potential for limited applications that align well with the objectives of blockchains, but not all of them, or not all that are being considered now. To give one example, elections are one application that's frequently hyped up in the press and in the communities of these projects, which I'm deeply skeptical that will ever see the light of the day. So, and of course, if you are interested in contributing to these projects or investing your money in cryptocurrencies, no matter where they come from, watch out for scams and hype and projects that promise much more than they deliver. So it's a design space that you really need to be careful about and exercise your caution. So I'm also always interested in what brings you or your interest to blockchains. So you can also write in the chat why are you interested in the topic, that I can take a look afterwards. So I'm also here representing the Blockchain Academy Network. This is a 2-year project here at Aarhus University, but in collaboration with many entities across Denmark. And there are many objectives to this project. The main one is technical education of professionals. So we are preparing and conducting online courses for on the space of blockchain technologies and distributed systems. We are also developing research use cases that demonstrate the technology and how to construct some of the building blocks in a secure manner. And some of the partners are also conducting business education for executives and also trying to develop or think of how the technology will affect the future. And lastly, one objective of this project is to assemble collaborative networks for companies interested in the technology and deploying it in their own products. So if you are, if this captures your interest, you can go to our website and take a look at content that's being added there. The project is running for a few months now, but its content will be increasingly made available at that website. But you can also feel free to contact us for questions and resources. So in this particular talk, I will start from the ground up. I will give basic definitions and try to at least characterize what applications make sense for blockchains. And I will use Bitcoin as a basic inspiration. I won't talk that much about the specific details of Bitcoin, but I think it illustrates very well the different layers that I like to structure, or we at Cobra here like to structure a typical blockchain. And then on the second half, I will talk about the consensus mechanisms and smart contracts, which are the upper layer, let's say, in terms of abstraction. So what's proof of work and what are the alternatives and how smart contracts operate. So if you think about a protocol stack as we think about TCP/IP, I like to see blockchain technologies as this sequence of layers. So of course they operate over the internet. We assume some open network that nodes can join and exchange messages through there without many guarantees in terms of security. So first thing that any blockchain project needs to establish on the internet is a peer-to-peer network for exchanging messages and for nodes to find each other and hopefully to become or to stay cohesive, so it doesn't split even by accident or caused by some malicious set of parties. So if you can establish a peer-to-peer network with many nodes, then you can also establish some kind of identity and try to send and receive transactions through those identities that could include currency, but also could include other pieces of data. Blockchains are not necessarily about money or payments. You can think about transactions as adding records to some kind of database. There are many, or sending files to be backed up. You can think of transactions in a very abstract way. But of course, since this is a network with nodes that are not per se trusted, we don't know which of these transactions are valid or not. So we need some consensus algorithm to separate which transactions make sense and which transactions are invalid or can be even malicious. And on top of the consensus layer, we can actually run programs on a blockchain. And these are called smart contracts, or the execution layer in some other texts. And the idea is you can store state and code on the blockchain and use the consensus algorithm to execute that code correctly and try to update the state as the different parties interact with that piece of software. And this can be quite powerful. And on top of all of these stacks, you find the applications. So in this talk, I won't talk much about applications. Again, I'll just characterize what some of them might look like. I'm interested in the technical objects that compose the middle layers. So what's a blockchain? First of all, it's a global ledger. So it's a history kept decentralized and stored by many nodes, which contains sets of sequential transactions. So you can think of a financial ledger in which you append different transactions in time on a global scale. It's also fully programmable in the sense that you can write software that can manipulate or can issue transactions to that global ledger. Some of these transactions will be deemed valid and then will be included in the ledger. Some of them will be deemed invalid and then be ignored or rejected. And this happens in a decentralized manner, again, because we have nodes operating over a peer-to-peer network. So the consensus layer will help deciding which transactions are legitimate or not. So if you have all of this together, then you have a blockchain, especially for money. You have something similar to Bitcoin. And the enthusiasts really think that this is a piece of technology that wasn't possible to build before, and that's somewhat true, although it builds up on developments from previous decades, both from the cryptographic point of view and distributed system point of view. Bitcoin is the first time you see these different ideas combined together. And if you look at the history of e-commerce or payments through the internet, you see several game changers across time. So basically the existence of local networks and TCP/IP made the beginnings of electronic commerce possible in the sense that nodes could communicate over some network across large distances. Having HTTP and SSL as a standardized protocol allowed these nodes to further send transactions for payments using credit card. And maybe the most popular way of sending financial transactions over the internet is PayPal from the 90s, that's still under operation, and recently actually announced that they will include support to cryptocurrencies soon. So they are also jumping on this bandwagon. So Bitcoin then, after it was proposed in 2009, adds a new piece in which we can do this, but without relying on a centralized authority or a company that will operate the network and will actually decide what transactions are valid or not. So the whole point of Bitcoin is to not trust a company like PayPal or Amazon or any other provider that could process payments. But for it to be useful, there are many requirements. It needs to be fast, or as fast as possible, or fast as interesting for the target applications. It needs to be secure for some sense of security. You always need to relax some of the security definitions when you think of a decentralized system. It needs to be cheap to run. So if it's too expensive, simply there won't be, there won't be many nodes. And it needs to be both easy to use, so users can find it familiar, and usability must be provided, of course. So users without technical or expertise in this technology can still be able to use it. But also, very importantly, it needs to be legal. So it needs to be compliant with regulations, no matter the market blockchain applications are being deployed on. So otherwise, of course, how the dissemination of the technology will be deeply affected if it's just illegal in some territory. So to go a bit further on the direction of giving a definition, to refine it a little bit, it's a ledger that's append only. So new blocks containing new transactions are always appended to the end of a blockchain. So they authenticate the transactions and blocks that come before, and they include new information that will be authenticated by the next blocks. So it's common to classify them in permissioned or permissionless. This refers to who has the possibility of issuing transactions and adding blocks to the blockchain. A permissioned blockchain is one in which there is access control in place. So only authorized nodes can issue transactions or can validate transactions. In a permissionless blockchain like Bitcoin, any node can participate and try to issue transactions and even collaborate for the blockchain to actually grow with new blocks. So I tend to prefer permissionless blockchains as a technical topic because I think it's where the interesting applications are. And some researchers that are even more skeptical than me would call a permissioned blockchain just a decentralized database. So it appears to be much more complicated than it needs to be for the applications of permissioned blockchains, but that's another debate. The whole point also is for it to be auditable, especially in the case of Bitcoin. So you have integrity guarantees because, well, if a block is added to a blockchain with a certain set of transactions or pieces of data, this will be stored there for as long as the blockchain project is alive. So it also provides tamper resistance in the sense that future blocks authenticate old blocks. So it's not feasible to change old data, to replace old data with corrupt data, because this will be detected by the network and rejected. Records are then authenticated and become immutable by this process of append-only extensions of the blockchain. And again, it's decentralized. There is no coordinating server that has a unified view and decides who can participate and what transactions are valid. This is reached by consensus in a decentralized manner, which means that consensus must work across mutually distrusting participants. So you don't have any trust assumption on the nodes or the miners or anyone collaborating for the blockchain to work, or the nodes running computations stored in smart contracts. This is, nodes are assumed to be adversarial, at least a significant fraction of them. So why a blockchain? When is it useful? So deploying an application on the blockchain pays a price, the price of decentralized consensus. This is a hard problem to solve, achieve consensus with a distributed set of nodes, agreeing on data across a distributed set of nodes, some of them potentially malicious, is a hard problem in computer science. This is characterized as the Byzantine general problem, in which there are several generals that need to decide if they will attack a certain target or not. But the generals do not know who among them are traitors. They cannot be trusted. They are malicious. They are under control of some adversary. So how can they coordinate the attack in a meeting time and positions from which to attack this target if some of them are malicious and might not even show up on the attack day? So this is an abstraction of the problem we study in computer science. And the result from theory says that large known fraction of these generals actually need to be honest and loyal, need to follow some protocol. Depending on the settings, this can be at least 2/3 of the generals, which is quite a lot if you think about a large network distributed across the internet. So running a protocol to achieve consensus on this set of conditions is computationally expensive, and also expensive in terms of both energy consumption for Bitcoin, but also bandwidth, because, well, you need to exchange messages and to broadcast across the network, distribute data, and so on. So applications running on the blockchain will be, by definition, expensive in several senses. So it only makes sense when you have the conditions for this application to fit or to align with a blockchain technology that you should be able to think about the idea. Otherwise, it's just overblowing something that can be much simpler. So what applications make sense? Those that need to store data of some kind on a distributed network, that perhaps needs to resist some kind of censorship by using nodes without any trust relation and distributed across the internet in different legal jurisdictions and so on. And this data should be hard to agree upon. So think about pieces of data in which it's not trivial to reach consensus, because, for example, it's not just public data that's trivial to verify or to authenticate. Although it's harder and harder to, even the news cannot be just referred as easy to authenticate anymore due to disinformation campaigns. But assume some collection of data that is hard to agree upon, assuming adversarial participants. So one easy example, financial transactions. Of course, financial transactions are hard to agree upon, because if you allow the nodes to decide individually which transactions are valid, they would just pick transactions that make them rich. So you need a way to check which transactions are make sense or not. Nodes will try, for example, to spend money multiple times if there is no need for the other nodes to agree on that set of data as legitimate. So other problem spaces in which the researchers have found solutions or found applications of blockchains are energy auctions. So think about decentralized production of energy, where most homes, most houses on the city have solar panels, and they actually want to sell the surplus energy to neighbors, or maybe back to the grid. You need now to decide the price, and the price fluctuates with demand. So one possibility would be to organize an auction with in some time period to actually decide a price for those surplus energy capacities. You can also think about government records when they involve multiple agencies and branches at different levels of government that maybe are hard to agree upon, like land registry, if it's an area that's under a dispute, for example, in some place. Supply chains involving multiple companies in multiple countries too, with different import and export restrictions, can also be seen as data that's hard to agree upon. Copyright claims, because, well, they by definition create attrition in the sense that multiple content providers can claim copyright, and you need a way to settle which of these are legitimate or not. Same applies to identity management and file backups. So these are some of the areas in which there are blockchain startups or companies that are providing interesting services and somewhat doing well. And I think they fit the characteristics of what we expect of a blockchain application. But again, only time will show which of these makes sense and which other application areas can also be interesting. So to give some foundational aspects before we start talking about consensus algorithm and transactions, I think it's useful to discuss what cryptographic ingredients we need to establish a minimal blockchain. And actually, there is not much you need from cryptography. You basically need hash functions for traditional proof of work to solve puzzles. So you probably know that the hash function is a function that's hard to invert, in the sense that they compress. There are lossy functions that take arbitrary amounts of input and compress this input to short fixed length output, in a way that, given the output, is hard to find one of the possible inputs. And this can be used to construct hash puzzles to prove to the network that your node spent some computational effort. So this protects the network from floods and floods of malicious transactions or fake transactions, as we will discuss later. And the other ingredient we need is digital signatures, because, well, when you issue a transaction, there must be a way for authenticating that this transaction comes from a certain user, and to verify that multiple transactions belong to the same user and they are spending money that was received before. So we need also to sign transactions or to sign data for authentication purposes. So just to recap some of the definitions, we need a cryptographic hash function that comes in other settings fairly naturally. That's pre-image resistance, that given an output is hard to find one input, or given an output and one possible input is hard to find another input that actually collides or produces the same hash value. We also need collision resistance. That's typical for hash functions used in digital signatures. It's hard to find two inputs that give the same output. And these are very traditional from cryptography. For blockchains, we actually need two additional properties. One is avalanche effect. Typically, this is if the hash function satisfies the first three, it also satisfies the following two. But it's good to enunciate them explicitly. So if bits of the input, even a small number of them change, or just one of them changes, the output of the function will change half of their bits, which means that the output can be seen as a pseudo-random. So just a small change in the input changes most of the output. So that the function propagates this change to the output, and this is important for it to be hard to invert. And it should be also puzzle friendly. So knowing the hash value of some input and some even bits of the input should still be hard to compute the rest of the input. So this is what allows actually hash puzzles to be constructed for proof of work mechanisms. You need to find an input that satisfies some characteristics of the input, of the output after processing through the hash function. So hash functions find many applications in cryptography. We use them to store passwords, to check integrity of files, to construct puzzles, as I said, to do hash-based commitments and digital signatures. So they are the Swiss Army knives of cryptography. They are used everywhere, and blockchains are no different. We also need digital signatures. On a digital signature setting, you assume there is a public key and private key pair, which are generated from a large space uniformly. Sampling from according to the uniform distribution. And this private key and public key have some special relation to each other in a way that someone can compute an authenticator from a message in the private key. And this authenticator, a signature, can actually be verified publicly by just the public key and the message. In a way that's hard to find the private key from the public key because the public key is meant to be public. All the valid signatures should be verified. It should be hard to forge a signature with a private key that you don't know. And these pairs do not repeat. So you can actually identify users by just their public keys because the space is large enough that they won't simply be sampled equally. So it's probability of two users generating the same public and private key pairs is just negligible. So in a decentralized system like Bitcoin or blockchains, where there is no authority issuing certificates to identify users, we can actually use the public key as identity. And that's one of the interesting aspects of blockchains. So now these are the ingredients. We need these two basic building blocks for establishing a minimum blockchain. And perhaps because doing financial transactions without relying on a centralized authority is a very hard problem across the internet. Bitcoin was the first application of a blockchain that actually got some traction, but it's not the first attempt of building something like this, some kind of electronic cash. So the most, I would say, well-known attempt before Bitcoin was DigiCash in the 90s, in which users would go to a bank and obtain some authenticated token from the bank. For example, issuing 5 electronic coins, some kind of piece of data that gives the power to spend 5 coins. So Alice is interacting with the bank here to get one of these coins, and then Alice can receive this coin and remove some information from the coin that make it hard for the bank to trace where the coin is being spent, because, well, any attempt of doing electronic money over the internet should try to approximate the the anonymity property of paper currency, so it's hard to trace. So after this happens, Alice can actually pay a merchant with this coin, and the merchant can check back with the bank if the coin is valid in some way, and that it was not spent before, because otherwise one user can just re-spend money as much as possible and then create problems. So notice that this was a product designed in the 90s, but still relied on a centralized authority to issue coins, which probably undermines the utility in practice, because, well, if you need a centralized authority to issue coins, you actually have a bank. So why building that, and what are the incentives for industry to adopt that? So Bitcoin, the biggest innovation is actually being able to allow something similar without relying on this centralized party issuing coins, and giving enough incentives for adoption from industry and users. So we start from the peer-to-peer layer, which is the ground layer of Bitcoin. This is basically connections between nodes on the internet. So these nodes or these connections transport protocol messages from the upper layers. And of course, these are established somewhat randomly. So nodes find other nodes through some kind of registry, and there is no centralized control of what connections can hold or not. So which gives censorship resistance. It's hard to take off the whole network because it's just this mesh of random connections across nodes. Anyone can run a node, anyone can send a message. Transactions and messages are just broadcasts across the whole network. They might not reach all the network as the picture implies, but they will certainly reach a subset of the network, and that's sufficient for operating a blockchain. But that's interesting. Anyone can run a node, anyone can just join the network and send transactions and relay other messages from the protocol, and this will be broadcast across the network. But of course, because anyone can run a node, some of these nodes will just be malicious, and they can be arbitrarily malicious. There is no restriction on what type of malicious behavior these nodes can have. So for example, they can just drop messages or try to split the network in two, so they get some financial benefit of doing that. They might selectively censor some of the transactions as well. For example, they don't want payments to a certain address, so they might just try to drop transactions sending money to that address. So there are many malicious things that these nodes can do. This can also try to break privacy and try to find out which nodes are running which identities, and try to trace transactions through the network. So this is basically how peer-to-peer layer works in Bitcoin, as any other peer-to-peer network. On top of that, we can establish identities. So different nodes that send transactions to the network, they have addresses which are hashes of a public key for a specific digital signature algorithm called ECDSA, using some elliptic curve that's not relevant. But what's interesting is across time, multiple transactions issued by the same node will be signed with the private key matching that public key. So transactions are linkable. You can sense that, you can see that, oh, those transactions come from the same node, and actually they are paying money that this node received on a previous transaction, which means Bitcoin is not anonymous, it's at most pseudonymous, in the sense that nodes establish a pseudonym on the network by being identified by them, their public keys, but you can still trace different transactions from the same node across time. So the only anonymity provided by Bitcoin is in the sense of linking pseudonyms on the network to actual identities in real world might be hard if there is some precaution, some operational security exercised by this node, but it's not something that comes from the protocol. It's just good operational security. And there are many nodes running Bitcoin. There are many Bitcoin nodes which are public. For example, if a certain NGO is receiving donations through Bitcoin, they need to publish their Bitcoin address. So you immediately link that address to that organization. So it's not pseudonym anymore. But this is just one approach. There are other blockchains attempting different levels of privacy. There is Zcash, for example, in which nodes are actually private and transactions are encrypted, both in terms of destination and sources, but also the amounts. And everything is verified cryptographically in zero knowledge for making sure that transactions are authentic. So it's quite interesting. But then there's the other extreme, when you have fully private transactions. There are several possibilities in the middle. For example, you could have some identity that's verifiable off-chain by some real-world authority that needs to comply with regulations, but also is represented on-chain in some privacy-preserving way, in a way that this privacy can be revoked in case this identity is shown to be misbehaving. So that's actually the design that the Concordium project developed in conjunction with Aarhus University researchers is going to be compliant with regulations. But this is a major problem in research and practice, how to balance these privacy concerns. You want to approximate real world money as much as possible while preserving some accountability in case things go wrong. So in the case of Bitcoin, transactions are just operations transferring currency between users that are digitally signed, and you still have a necessity of creating money in the network for it to be spent. And this happens through a process called mining. So essentially when nodes want to issue transactions, they broadcast those transactions to the network. And then some other nodes that are miners, they will just collect these transactions, solve a cryptographic puzzle, and add some reward as a form of a transaction, a coin-based transaction, receiving money from thin air, in a sense. So in this case, there is a block here with several transactions. So Alice is trying to, Alice is the miner. She's trying to both spend money and also allow others to spend money. So you can see that this miner is creating a transaction here that rewards 25 coins, 25 pieces of currency back to Alice. So if the hash puzzle, the cryptographic puzzle that's solved by this miner is deemed as correct by the other nodes in the network, this block will be included in the blockchain, and then Alice gets more money. So the interesting part is there are no explicit coins as in the DigiCash example. There is no bit stream that is a coin that you spend by sending someone else. Actually having coins is having a positive balance stored in the ledger by considering all the transactions that involve that node or that public key. So if there is more money coming in to that public key than being spent by that public key through digital signatures using the matching private key, this means that this node has a positive balance. And if this is a miner, the miner is allowed to collect rewards by spending effort to solve these cryptographic puzzles. So this is perhaps a more explicit picture showing how the blocks look like. So it's again the blockchain. So there's a sequence of blocks here. There are sequence of blocks, all of them time-stamped, and they have the hash of a previous block. So when a new block is added to the blockchain, like take block 12 here, there is a hash of the previous block that contains a hash of the previous block and so on. So if there is a malicious attempt of changing history and changing the transactions included in one of these blocks, this hash chain will just be invalidated, and this will be detectable by the network and then rejected. So the blocks also contain unknowns that's part of the cryptographic puzzle. We will discuss this in a little bit, but basically it's the input of the hash function that needs to be found for the puzzle to be solved. And then each individual block has a collection of transactions you can see here that are stored in something we call the Merkle tree. So it's a data structure. So the root of this Merkle tree is stored on the block to authenticate all of these transactions. So this is just a cryptographic data structure that allows to very efficiently authenticate all these transactions by just verifying that the root is correct. So each block has metadata authenticating previous blocks and some data adding new transactions to the blockchain that will be authenticated by future blocks with hash in the hash chain. So, so these are how transactions look like and how they are stored in the block. And as I told you, transactions are broadcast across the network. But of course, there are different latencies and different network organizations that will prioritize some messages over the others. So transactions arrive in different orders. Some of them might not even arrive to all nodes. So it's hard for a node to get any unified view of the network. You actually get something close to the picture that some nodes will see the green message, some others will see the red message, some of them will see both, but in different orders. So we need a way, or in the consensus layer is responsible for creating or deciding what's the uniform view that all nodes, or at least all honest nodes, need to agree with. So in a way, it establishes a unified view of this. of these transactions. And as I told you, there is no centralized node, or there is no election protocol that will elect a centralized node to decide what's correct or not. So what actually happens is there is a lottery. So nodes are trying to solve this cryptographic puzzle, and whoever solves this puzzle in a certain point in time gets both the reward for solving that puzzle as a mining operation, but it also decides what's the new block to enter. And this puzzle is designed to be hard to solve, so you need to spend resources to solve it. Otherwise, there would be multiple winners all the time across the network. It would be hard to just pick one of them to be the leader to decide what goes in as a new block on the blockchain. There is a sort of lottery process that randomly picks a node by just having many of them solving cryptographic puzzles. And then if that happens, the view of that node, the transactions received by that node, and some reward for running this computation will be added as a new block to the blockchain. So that's the incentive that keeps nodes trying to solve these puzzles. Giving rewards to nodes that collaborate with computational power to extend the blockchain is the main incentive. But this must be decentralized, right? So otherwise there is a single point of attack. There are nodes coming in and out all the time, but the incentives should go to the honest nodes. And in a way that a solution to the puzzle needs to be very easy to verify. Otherwise, it's very inefficient. So Bitcoin uses a proof of work consensus. So there is a current difficulty level that increases with time, and the whole network agrees on a puzzle. There is some target of the computation Y, and the participants must find some input to hash function that the output is smaller than Y. And the solution is of this form. There is a set of transactions that were broadcast by the nodes. There is a Coinbase transaction giving reward to the miner, and there is a nonce. This is the variable part of the input that the node needs to try many candidates until finding the correct one that satisfies this restriction. So, and this will be processed by the hash function, of course, and it needs to target that difficulty level. So the nice thing about this is it's expensive to solve. You need to try many of these nonces to find the right one, but very easy to verify. All the other nodes in the network can just compute one hash value to verify that this is a proper solution. So that node deserves to receive the reward. However, imagine that there is some temporary instability of the network. Some nodes might not be connected anymore. The network might split in different subnetworks. And again, we have a problem of consensus. How can you reach consensus if nodes are seeing different pieces of transactions or different sets of transactions, or even more worryingly, if there is a fork? There are two nodes at different points at the network that are in these different subnetworks split, which mine some block at the same time. And then is when the consensus algorithm really is important. If the network is unstable, you might have a fork, and then you might have different sets of nodes seeing different branches. So here you could see that the one part of the one subnetwork could be seeing these blocks as the legitimate ones, and the other part of the network could be seeing could see this other branch as the legitimate one because, well, there were two different miners finding these blocks at one point in time. So Bitcoin decides that whoever or the branch that grows further becomes the legitimate one by a difference of at least 2 blocks. So if this happens, the branch that will be the correct one is the longest one. But the problem arises that imagine that a set of malicious nodes actually calls a network split and mine on this branch of the network on purpose, so that this branch is confirmed and the transactions on the other branch are just rolled back. They are canceled. This will be an opportunity for double spend attacks. So nodes could include their transactions, financial transactions on both branches and mine one branch adversarially, maliciously, such that it's extended and cancels the other one. So then the money would be rolled back, but then, well, the purchases were already performed. So this would be a double spend attack. So the Bitcoin assumes that at least half of the network is honest. They will follow the protocol such that this situation is not a problem in practice. But it's important that applications running or interacting with blockchains really need to wait for transactions to be confirmed which take a long time until you get evidence that the branch in which this transaction is included will be extended by a certain number of blocks, at least 2 blocks in the near future. So this is a problem called finality. There are also cryptographic solutions for solving this elegantly that are deployed in some projects. There are problems with this approach. It's very inefficient in social terms. Solving these computational puzzles does not help humanity in any way. It's just computing hash functions, right? And lots of energy is spent just doing that, doing this useless computation from the point of view of humanity. And actually it becomes a competition of who can solve more hash function evaluations on a certain point in time, which leads to special hardware, mining pools and large large infrastructures of equipment, which end up being centralized, just dedicated to this mining process because it's the profitable piece of running the blockchain. So you can see here a picture of just a large mining pool of dedicated hardware and mining all the time to collect the rewards and invest more in the mining operation. So as a result, Bitcoin is consuming a huge amount of energy because of the proof of work mechanism. And it's not only a problem of energy, as I said, it's also a problem of centralization. We're supposed to have a decentralized network, but a small number of miners in the Bitcoin network actually hold most of the computational power that extends the blockchain. So this is a problem from a decentralization point of view. It's not something we want. The whole point is to have a decentralized network. Even more worryingly, many of these miners are located in China because of energy subsidies. So it's certainly a situation you don't want to be. So an alternative to proof of work is what we call proof of stake. It's still a lottery among the nodes that want to participate. It's just organized differently. So each participant in the network needs to have some account with a balance. And then the participants can give some of their money as a stake, which increases the probability that they actually win the lottery. So you can assume, again, some cryptographic puzzle that's much easier than in proof of work, but still needs to be solved. And the more money a participant puts on its attempt to solve the problem, the higher the probability of solving the problem the node gets. So it gets some advantage. And it still takes into account small users without much money, without much balance to have at stake and try to win the lottery. So small users which do not have a huge investment can still delegate the small stake they have to other users so that they still participate in some way. And now the assumption is a bit different. Instead of half of the nodes being honest and mining on the chain that's longer, now most of the money in the system is honest. That's the assumption. Otherwise, nodes will not actually dedicate some of their investment to just grow the blockchain. It will not be a rational decision. So this gives some advantages. Both approaches lead to centralization, of course. You centralize mining power or stakes on certain nodes, but proof of stake deals it with in a much cheaper way. So you don't have the energy consumption. And in theory, because the puzzles are easier to solve, you have higher throughput, so you don't need to wait that much time for transactions to be finalized. But there are trade-offs. So proof of work, we know it works in Bitcoin. It's very expensive, but it kept the network operational for more than 10 years. Proof of stake is still being deployed, still unclear how it will behave at scale because it's much harder to analyze and calibrate incentives for. These are not the only ways to build consensus. There are many, many other ways. I won't mention all of them, but there are all sorts of different, both research works and also attempts to deploy this in practice that think of consensus in a different way. But in all of them, you need to find some problem that's non-trivial to use and that nodes can solve and prove to the network that these problems were solved in the correct way, that the network can verify and then give the rewards back. So we talked about consensus algorithms. So the consensus algorithm decides what transactions are added to the blockchain. But this is still a payment system. We don't have anything more powerful on top. And this comes with smart contracts. So basically, smart contracts are programs stored on the blockchain because, well, to run programs, you need a description of the computer program in some language, right? And state. So you can store both on the blockchain, both the code to be executed and the state of that program in a certain point in time. And then you can trigger the execution of that program and update the state accordingly as computer programs run on individual machines. The only difference here is because it's stored in the blockchain, you can rely on the consensus layer again to decide what's the correct execution of that program so that the state is correctly updated as well. And the idea is to automate contracts. So if you have a set of conditions that need to be met for a result to be triggered, this makes total sense for deploying as a smart contract because, well, you can formalize this contract as just as a computer program with several advantages. So you don't need intermediaries, you don't need scroll, you don't need centralized parties again. It's self-enforced by the nodes running the blockchain. The state is public and stored in the blockchain, so it can be verified. The consensus algorithm will actually dictate what's the correct execution of the protocol. Again, by spending redundancy and spending resources across all these nodes running the program, but that's the cost of decentralization. So you can think as a, probably the easiest real world analog is a vending machine. So there are simple conditions for triggering the result, which is issuing a product that was just purchased. So in a vending machine, you have a very clear defined protocol. You insert the money, you pick the choice. If these conditions are met, you get the product. So this is the simplest, I think, example on the real world that can be an analog of a smart contract. So why the name contract? Well, we're trying to automate and translate guarantees we get from physical contracts, where you have parties agreeing on terms and on conditions that and results that will be met when these conditions are satisfied, and you translate that to a set of programs stored in the blockchain that still have conditions and still have results and still involve interactions between multiple parties, just with lower costs in at least hypothetically, because you don't rely on arbitrage or legal systems to actually decide what's legitimate or not. This is all enforced by the code that runs in the smart contract. So maybe a very clear example is crowdfunding. So we have a set of terms and conditions that are very clear. Donors will donate money to this initiative. If conditions are met, then the money is sent to the project. If the goal is not reached, the conditions are not met, the money comes back to the donors. That's the simplest example I can think of a functional smart contract. Because, well, the conditions are very clear. A certain goal needs to be reached. It's very clear where the money goes if the goal is reached or not. And decentralization is great because you don't have a single party actually dictating if the money will actually go to the project or not. We all have heard of different crowdfunding scams where people donated money that went nowhere. So this could prevent that from happening. So Ethereum is an example of a platform where smart contracts are functional and already being deployed in several applications, although there are more like prototype, I would say, at this stage still. But we get, by running smart contracts, several advantages. I mentioned some of them before, but there is no need for third parties. The contract is immutable and run automatically as it's triggered by the users of the smart contract. Which leads to savings in money and higher precision. There is no, there shouldn't be ambiguity of what should happen. This is all formalized in code in a way that can be auditable as well. A problem, of course, is legal status is unknown. It's not yet tested anywhere. I don't know of, for example, any attempt in Denmark to verify that this would hold in court. And there are trade-offs too, because the code is immutable. Vulnerabilities are very hard to fix. The code is already there and can be abused and can be exploited by anyone with access to the blockchain. So there is still much work to be done on verifying the correctness of those and making them more adopted. So as a final word, there are many research challenges in this space. Some of them are being tackled here at the Aarhus University Cobra Research Center. Many of them lead to privacy and security issues, how to design them in a privacy-preserving way, how can we accommodate regulators and regulations, how can we analyze the different consensus algorithms and make them private or not, can we formally verify smart contracts, can we make them private so they don't leak sensitive information, sensitive financial information of the parties interacting through the contract. What about legal systems? Can we change information after reaching consensus on the previous history on the blockchain to maybe update or to remove information that's illegal? All of these are questions that are hard to solve in practice and are being studied here in different capacities. One interesting problem is how to perform governance. Instead of relying on a set of developers that develop the blockchain software, can we create conditions for the blockchain decide itself what's proper and what's not proper? So there are projects also tackling that angle. In terms of performance and scalability, one interesting development from here is a finality layer that achieves robustness, that verifies and finalizes transactions efficiently, even when the network is not behaving well, because it's, well, miners are, or in this case, it's more designed for proof of stake. When many blocks are being added to the blockchain or not enough blocks are being added to the blockchain for it to be functional, you can still get finalization and finalize some of the transactions. A big question in the whole space is it possible to scale blockchains such that they become as fast as credit cards? Probably unlikely because of the cost of decentralization, but it's certainly a goal to maximize throughput as much as possible, and also to reduce storage, because, you know, many nodes need to store a non-trivial fraction of the whole set of transactions, and this takes quite a bit of space. So all of these are interesting, relevant research challenges. If you are interested in working in some of this, get in touch and maybe apply for our PhD program, or maybe we can have a joint research project with parties in the industry. But also there are many blockchain projects tackling similar questions. I give names and examples here. And I'm almost over time, or maybe a bit over time, and thanks for your attention.
You're pretty fine. It was a 1 hour presentation, so you have 10 minutes of questions. So thank you for the presentation, Diego.
Thank you.
It's question time. So if you have questions, please write them in the group chat. And so Diego can actually answer right away. Or if you want also to talk, I think, with Diego later during the lunch break, Diego, I guess you'll be available also in the Gather the Town. So if someone wants to approach you, they can reach you there. Or
yes.
Perfect. So just I will start with a question waiting for the others. So you say also in the last slide, you mentioned a lot of research problems that still need to be solved, especially like scalability. And you mentioned that even the case of the credit cards, probably, and if I quote you, it will not happen because will not reach, or at least it's computationally be expensive to be able to have a blockchain to handle the credit cards. So right now, what do you think in the next 5 years, what kind of application domain will blockchain be deployed, and will we need to solve this research challenge before having like a huge, large adoption of blockchain projects?
Yes, so I will answer the second question first because I think it's more natural. I think scalability and privacy need to be solved in a, especially a regulation-friendly way for adoption to increase. Or otherwise, it will stay as a niche technology for privacy enthusiasts, right? Which are willing to pay the price of horrible scalability to operate across government boundaries and so on. In terms of, so the second question, I think, yeah, we need to solve this too. In the next 5 years, I would say that financial transactions and payments are still the main drivers of both adoption and new projects, because essentially these are the applications in which the incentives are very clear, right? If you deploy a project that solves problems in that space, it's easy to make money because, well, it's the financial space, financial technology. So this leads many groups to just work on this topic. So certainly we will see in the next 5 years lots of development in that way, which will take different approaches to the problem. So I hope in the next 5 years to see, for example, more private cryptocurrencies. We have just a couple now with different trade-offs. So I mentioned Zcash already. There is Monero. Concordium is trying to do something similar, but in a regulation-friendly way. and this application translates very well real world needs. So I think it's very natural. It's not a coincidence that Bitcoin came first and still is around. Other applications that I see in the next 5 years, maybe becoming more popular are supply chains, because I think this is a big problem with counterfeiting and goods moving across borders and being hard to authenticate, especially in these crazy times, right? We have governments stealing large collections of masks and supplies to other countries. So we need certainly a better supply chain, a global supply chain that can be verified, and this could be in principle be helped by a blockchain. So that's one problem or one application that I think will lead to more adoption and projects in the next 5 years. But certainly financial transactions is still the main, in the short term will be the main driver.
Thanks for the questions. I don't see any other in the chat, but I'm also interested, well, I have another one. About before there was also a question on like the risk for democracy, and I actually wonder if, for instance, we are starting to use blockchain to register or somehow to conduct certain activities connected to like voting or possibly like activities connected with being active in our democracy. And one of the things that blockchain bring forward is that is like sharing is democratic. But if you're talking about states, also it could be, I could imagine Denmark has less than 6 million people, and if you create like a blockchain with will in a way be subject to the decisions of China, for instance, where they have like millions, billions of people, and then they can somehow get control of the blockchain simply because they are more and then they can control the nodes and steer the blockchain away. Do you see any potential applications of blockchain, for instance, for elections or for things connected to expressing opinions in a democratic way?
Yes, I'm, as I said in the beginning, I'm deeply skeptical because when you disseminate news or official information backed by authorities, or you collect votes through a blockchain, you're basically opening these two public pieces of the public sphere to external interference, right? So now you have much more powerful and numerous nodes interfering with what news are legitimate and what votes are legitimate. It doesn't have to be about, for example, manufacturing fake votes or changing the results. It could be just preventing people from voting or preventing people from receiving information from the government or health authorities. So it can be just a denial of service attack that can be easily mounted from the outside, but just throwing bandwidth at that specific project interacting with the blockchain and then censoring or preventing people from, both receiving information and sending transactions that encode votes or news updates. So I don't see blockchains actually being used in the short term, if ever, for these applications, exactly